Hello everyone, happy that you are still here all. So I will be talking about velocity selective ASL at 7 Tesla. And I will first start with the difference between the ASL sequence that we're using. So we've seen a lot of pCastle the last coming days. So there you label in the neck region and image in the brain. And you do that once without labeling, and subtraction of these two results in a perfusion image. Then there is pulsed ASL. In this case here, I have a fair, so a selective and a non-selective inversion, and the subtraction of these two also results in a perfusion image. And then lastly, there is velocity selective ASL, where you do a velocity selective module where you crush the fast flowing spins, and you also do that once without the gradients, and then you also get a perfusion image. So why would you want to do velocity selective ASL at 7 Tesla? And I hope to convince you about that. It's actually useful. I want to use it for fMRI purposes, and maybe also for white matter imaging, for example, because you're insensitive to ATT. And I think I've seen over the last few days that ATT can be a problem in white matter. So I will be focusing on velocity selective ASL. So the challenges in general for ASL at 7 Tesla, one of our colleagues there wrote a nice review about that already 13 years ago. So at 7 Tesla, there are a lot of B0 inhomogeneities, especially around the ear cavities, and also in the neck, so where normally pCastle is labeled. Second of all, there are a lot of B1 inhomogeneities. So the wavelength of the RF pulses are much smaller at 7 Tesla. So you see these dips in B1 in the temporal lobes. And besides that, we also have a problem with B1 coverage, because we are using the two-channel transmit head coil of NOVA. There's almost no B1 coverage in the neck region, where pCastle is normally labeling. Also, physiological noise almost goes with the square of the field strength, so becomes also a big problem for ASL. And also the SAR. So with higher field strength, SAR goes almost with the square and then flattens out a bit. But that will become a problem when I want to do fMRI, because TR will explode. And the short T2 of blood at 7 Tesla. It will become difficult for velocity selective ASL to apply longer modules, because you will lose label with T2 decay. But luckily, T1 is a little bit longer at 7 Tesla, so we lose less label because of T1 recovery. And for velocity selective ASL, we can actually create label in the sweet spot of this transmit coil, because we label within our region of interest compared to the other ASL techniques. And we are arterial rival type insensitive, because we label inside our volume. So how we want to tackle this? For the B0 and B1 inhomogeneities, use adiabatic excitation and adiabatic refocusing. Get rid of physiological noise, you want to use background suppression, but additional pulses, so that would increase the SAR, and therefore we want to use as low number of background suppression, also preferably. So there we need to find a trade-off somewhere. And to tackle the T2 problem, the velocity selective inversion that's normally used at 3T is not really applicable, because it, first of all, has a lot of flip angles, about 20 degrees, 180 degrees. It's not working with the B1 inhomogeneity that we have. So we're limited to velocity selective saturation, which also has a shorter echo time, and therefore there's less T2 decay during the labeling module. So we want to go for single refocusing velocity selective saturation, and then you're ready. Come to the BR4 module. So a quick explanation what the BR4 module is. It consists of 4 modules, well, the middle one consists of 2. So it's a first a 90-degree flip angle around the x-axis, then a 180-degree about the y-axis to refocus, and a minus 90-degree flip angle to flip everything back to the longitudinal plane. So effectively, the static spins are untouched, in this case, except some T2 decay. So in velocity selective ASL, we then apply some gradients inside to saturate spins moving about a specific velocity, because they build up phase. And then for a velocity profile, you get a a sync profile in terms of how much signal you crush for a specific velocity. If you then assume a laminar flow within a vessel, you get a sync pulse with the first zero crossing about that velocity cutoff. So how that works in velocity select ASL, we have our labeling module, label all the fast flowing spins, here represented by a cross instead of an arrow. Then we wait a little bit for the to move, so middle of the PLD, end of the PLD, you now see that the labeled spins have moved into capillaries, but we also still see that there's different here in the veins. So then we apply a vascular crushing module in both the control and the label case, resulting in a signal difference, especially around the capillaries. So that's nice for fMRI, that we're sensitive to capillaries. But there's also a little bit of T1 relaxation. So we don't have the full difference between label and control as we wanted to have. But because we label inside the region of interest, we can also scan with shorter PLDs because we're not sensitive to the ADT. Then I think this was introduced by G.R. Joe, that if you apply the last beer segment with 0 degrees phase instead of 180 degree, then you actually do a 90 degree pulse around the x-axis. You invert all static spins or flipping them back to the longitudinal axis. So this can create intrinsic background suppression without additional SAR. That can be seen here on the right, where on top is the normal velocity selective saturation. If you focus on red, it's just keep going up, it's gray matter. And here in the velocity selective saturation, where the labeling is, you see that the static tissue is inverted. So that gives us intrinsic background suppression at the moment of the readout. And we compare that to the fair ASL that is at the moment, I think, the state of the art at 7 Tesla. So first results of a quantification with the velocity selective ASL at 7 Tesla on top without the vascular crushing module. So you can clearly see here these draining veins still. And but after applying this vascular crushing module and therefore also be able to quantify it, you can see that we can have nice perfusion method velocity selective ASL with the expected range of about 60 milliliters per 100 grams of tissue per minute. In only about 3 minutes of scan time. Then I compared it to fair ASL, where if we compare the velocity selective inversion and the velocity the fair, you see that we see a lot more gray matter, white matter contrast in the fair ASL. That's also reflected in the TSNR. So the TSNR of the fair is still better than the velocity selective ASL. But it's hard to say for me now if the more contrast between white matter and gray matter in fair comes from higher TSNR or that we are more sensitive indeed to white matter perfusion now with our velocity selective ASL. But I have to scan more subjects for that to be able to confirm that. We also see here that in the velocity selective ASL, we especially have good TSNR posterior of the brain. That's mainly because of B1, because I used metamaterials around the head to homogenize B1 a little bit. But I could clearly see that B1 was best in the posterior lobes at the moment. So the use of PTX, which we didn't use in this project, could be of great help to improve B1 and thereby improving also TSNR for the velocity selective ASL. As I said, I want to apply it in fMRI. So we did an fMRI experiment in 2 participants, a flickering checkerboard, 27 seconds on, 20 seconds off, using surround subtraction and surround averaging to get the ASL weighted fMRI signal and the bold fMRI signal. And you can clearly see that we are sensitive to the hemodynamic response function, but SNR is still low. So we keep optimizing this by improving the background suppression and switching to parallel transmit to be able to do functional MRI using velocity selective ASL to be more specific to neuronal activity than, for example, the bold signal. So in conclusion, We showed the feasibility of velocity selective ASL at 7 Tesla, and I also hope that I showed you that it can be very useful for fMRI or for white matter imaging. For example, currently it still has an inferior TSNR to FAIR, but I also have to say that the FAIR there took more than 1.5 times as long as the velocity selective ASL because the SAR was much higher. So I had to add additional waiting time to be able to scan it. So PTDX could potentially solve our B1 issues, and we showed the first proof of velocity selective fMRI at 7 Tesla. Then lastly, I want to do some shameless self-promotion for the people from the Benelux here. So we organized the ISAMRM Benelux chapter annual meeting on the 8th of March. And with that, I want to thank you all. Also thank Alex for organizing this incredible meeting. And if there are any questions, I would be happy to answer them.